A few days ago, Russia reportedly tested an impossible missile, a missile that can fly just above the Earth's surface, avoid enemy radar, circle the planet for days, and strike its target whenever commanded. An extraordinary weapon. Because Russia has tested many new weapons during the ongoing years-long Russia-Ukraine war, the media did not give much attention to this missile test. Most people might think this is just another new missile. But this is not just another ordinary missile. This is a nuclear-powered cruise missile. Unlike normal missiles, it does not burn fuel to fly. It is powered by a small nuclear reactor. In other words, each missile is a flying nuclear reactor. That is why some people call it a flying Chernobyl. If Russia has truly done this, it is not just a milestone in missile technology. It is a major turning point in propulsion technology itself. Many countries have tried to build such a missile for decades. All of them abandoned the project halfway. That is why some people refer to it as the impossible missile. After hearing all this, a natural question will come to your mind. Normal missiles and jet engines move forward by burning conventional fuels and pushing hot exhaust gases backward. But in a nuclear-powered missile, fuel is not burned. So what exactly is being pushed backward to make it move forward? What is a nuclear-powered missile? How can a nuclear reactor generate thrust? What advantages does such a missile have? And did Russia really succeed? Let us find out. Hi friends, welcome to a new video from Science Simplified for All. On October 26th, Russian President Vladimir Putin announced the successful test of a new nuclear-powered missile called the 9M730 Burevestnik. NATO calls it SSCX-9 Skyfall. According to Moscow, a test flight on October 21st lasted about 15 hours and covered roughly 14,000 kilometers. Normal missiles fly using the energy obtained by burning some kind of fuel. Burning is a chemical reaction, and the amount of energy it can produce is limited. That is why long-range missiles need a huge quantity of fuel. In many cases, more than half of a missile's total weight is just fuel. Even then, most missiles only carry enough fuel to burn for a few minutes. Long-range missiles are mainly of two types: ballistic missiles and cruise missiles. A ballistic missile, after launch, quickly climbs to its maximum possible height, in most cases, even outside Earth's atmosphere. This stage is called the boost phase. When it reaches maximum height, the fuel usually runs out. After that, the missile travels the rest of the distance due to gravity and glide and reaches its target. Even the longest-range ballistic missiles carry fuel only to burn for some minutes. Their extremely high speed is what allows them to reach very large distances. Cruise missiles are not like that. They fly inside the Earth's atmosphere for almost the entire time. Many cruise missiles fly just 50 or 100 meters above the ground. Compared to ballistic missiles, cruise missiles are much slower, so they need to fly for a longer time to reach their target. I have already made a detailed video explaining the difference between ballistic missiles and cruise missiles, so I am not going deeper into that here. Those who are interested can watch that video. Today, even the longest-range cruise missiles can only fly for around 6 hours because they carry only the fuel required for that much flight. This is where a nuclear-powered cruise missile becomes completely different from a normal missile. It does not use chemical fuel. Its energy comes from nuclear fission inside a compact reactor. Nuclear fission produces far more energy per kilogram than any chemical reaction, so only a very small amount of nuclear fuel is needed. With that small amount of fuel, the missile can stay hot and generate thrust for a very long time. In simple words, a nuclear-powered cruise missile can fly for many days without refueling. That extreme endurance is its biggest advantage. You might now be thinking, why would a missile need to fly for many days? Russia's RS-28 Sarmat, also called Satan II, can reach almost anywhere on Earth in about 30 to 45 minutes. Then why build a missile that travels for days? There are 4 reasons for this. 1. As we said earlier, a ballistic missile goes extremely high during its boost phase. Because of that, enemy countries will know about the launch almost immediately. And after the boost phase, there is almost no propulsion. So the flight path becomes predictable. The enemy can calculate its trajectory and take defensive action to some extent. 2. There are several treaties signed between Russia and the United States. These treaties limit how many ballistic missiles each country is allowed to keep. But cruise missiles do not come under those limits in the same way. Since Burevestnik is a cruise missile, it is not restricted under those treaties for now. 3. The longest-range cruise missiles today have a range of roughly 3,500 kilometers. With that, you cannot reach every corner of the world from Russia. And increasing the range of a conventional cruise missile is difficult because it needs more fuel. But a nuclear-powered cruise missile has almost unlimited range. So it can reach any target on the planet. 4. Most missile defense systems find it difficult to intercept low-flying cruise missiles because they follow the terrain. Buildings, hills, forests, even the curvature of the Earth block radar signals. By the time a radar detects such a missile, it may already be too late. This advantage exists for all cruise missiles. But a nuclear-powered cruise missile has one more advantage. The range of a missile defense system is very limited. For example, the Russian S-400 system has a range of around 400 to 600 kilometers. Other well-known systems include the US Patriot, the US THAAD, the Aegis SM-3, and Israel's layered systems like Iron Dome and David's Sling. All of them have similar maximum range limitations. Even if a country installs many such systems, covering an entire large nation is impossible. So, defense batteries are placed only at important strategic locations. A normal cruise missile has limited fuel, so it usually takes the shortest route to the target. If a missile defense system lies in that route, it may not have enough fuel to detour. But a nuclear-powered cruise missile does not have this problem. Because range is not a limitation, it does not have to follow the shortest path. It can study the gaps in the enemy's defense network, take long detours, fly from unexpected directions, and reach the target safely. It can even keep circling the planet for days, wait for the perfect moment, and attack when commanded. In simple words, if a missile has unlimited range, the number of options becomes unlimited. That is why a nuclear-powered cruise missile is considered a major turning point in missile technology. A nuclear reactor is usually used to generate electricity. But how can a nuclear reactor create thrust for a missile? That is what we will look at now. Missiles, rockets, and jet engines all work based on Newton's third law of motion. For every action, there is an equal and opposite reaction. In a normal engine, the action is hot exhaust gases being pushed backwards. The reaction to that is the forward motion of the missile or aircraft. So if a nuclear-powered missile does not burn fuel, what exactly is it pushing backwards to move forward? To understand this, we need to slightly modify the way we think about how engines work. Let us take the example of a normal car engine. Air is drawn in from the atmosphere. This air helps fuel to burn. The burning fuel creates hot gases, and the pressure of these gases pushes the piston. This is the idea most of us already know. This is correct, but only partially. Atmospheric air contains about 78% nitrogen and 21% oxygen. We assume that oxygen is the only useful part of air because it supports combustion. But that is not true. Air inside the engine has another important role. It absorbs heat and expands. Even though nitrogen does not take part in combustion, it absorbs heat from the burning fuel and expands heavily. This expansion increases the total pressure inside the cylinder. So the pressure that moves the piston is not only from the chemical products of combustion, it is also from the expansion of the air that has absorbed heat. In a jet engine, this effect is even more important. A jet engine pulls in 4 to 7 times more air than what is needed to burn the fuel. Fuel burns, produces heat, and that heat makes the air expand massively. It is this huge volume of hot, expanded air that is pushed out the back of the engine to create thrust, not just the direct combustion gases. So, if we can heat the air and make it expand, Even without burning fuel, a jet engine can still produce thrust. And this is exactly the principle used in a nuclear-powered jet engine. A normal jet engine has 4 main sections. 1. Compressor section. Air is drawn in from the atmosphere and then compressed. This section is made of several rows of stationary blades and rotating blades placed one after another. Together, these rotating fans and fixed blades compress the incoming air. 2. Combustion chamber. The compressed air enters the combustion chamber, where it mixes with fuel and burns. 3. Turbine section. The hot, expanded air produced by combustion flows through the turbine. This fast-moving air spins the turbine blades, and the turbine, in turn, spins the compressor at the front of the engine. 4. Exhaust nozzle. Finally, the high-velocity air exits through the exhaust nozzle. The air rushing out at high speed creates the thrust that pushes the aircraft forward. Now imagine the same engine, but with one major change. In a nuclear-powered jet engine, there is no combustion chamber. Instead, there is a small nuclear reactor. The compressed air from the compressor does not go to a fuel-burning chamber. Instead, it is directed through the core of a compact nuclear reactor. Inside the core, nuclear fission releases heat. That heat makes the air extremely hot and causes it to expand. The expanded air then rushes out through the turbine section and finally through the exhaust nozzle, creating thrust, just like in a normal jet engine. So, the idea is simple. Replace chemical heat with nuclear heat. Everything else is almost the same. But then a question naturally arises. If the idea is this simple, why was it so difficult to build? Building a nuclear reactor for this purpose is not easy. First challenge is size and weight. Power plant reactors are very large and heavy. They cannot fit inside a jet engine or a missile. Shrinking a reactor so that it fits inside a missile is hard enough, but it must also be light and still deliver the required power. That means very high power density. Designing such compact high-power reactors is extremely difficult. Second challenge is temperature. In power plants, reactor heat is removed by water. The coolant temperature is usually below about 300 degrees Celsius, so the reactor core never gets extremely hot. But in a jet engine, the working fluid is air, which has a much lower heat capacity than water. To produce enough thrust, the air must be heated to very high temperatures, often above 1000 degrees Celsius. That means the reactor core has to run even hotter. Keeping a reactor core intact and functioning at such extreme temperatures is a major technological challenge. Only special materials that can survive both extreme heat and intense radiation can make this possible. Third challenge is radiation shielding. Civilian reactors use thick, heavy shielding to protect people and equipment. A missile reactor cannot use such heavy shielding because weight must be minimized. Even if no humans are on board, radiation from the core can damage electronics, navigation systems, and other components. So, the reactor needs effective shielding that is also lightweight, another very difficult engineering problem. There are many other technical challenges beyond these three. I have mentioned only the most important ones here. In the 1950s and 1960s, several countries, the United States, the Soviet Union, the United Kingdom, and France, considered building nuclear-powered missiles. The UK and France did not significantly advance those plans for reasons that are not fully public. The United States, however, pushed much further under Project Pluto. That program successfully built a nuclear-powered jet engine on the ground and tested it. But the US did not build a flying missile around that engine, and the project was later cancelled for a variety of political and technical reasons. The Soviet Union also tried to develop nuclear-powered jet engines in that era, but clear public data about how far they progressed is still scarce. Russia first publicly announced the Burevestnik program in 2018. There are reports that a test in 2019 ended in a serious accident. Some accounts say there was an explosion and a radiation spike, and that several scientists may have died. Because the details have never been fully confirmed, it is safer to treat those reports cautiously. On 26th of October 2025, Russia announced that a test flight of Burevestnik, conducted on October the 21st, had been completely successful. However, Russia did not release clear supporting data for this claim. That is why many in the international community remain skeptical. There are many critics and analysts who also warn about the serious risks of such weapons. In a nuclear-heated air-breathing engine, the air that passes directly through the reactor could become contaminated with radioactive particles. That means the missile might leave a trail of radiation along its flight path. Power plant reactors have many safety systems that small missile reactors would not have. Because missile reactors must be compact and lightweight, they lack the same level of protective systems. That raises the risk of a nuclear accident. Some experts have even called such weapons a flying Chernobyl. Another concern is crash site contamination. A missile that contains a full reactor will spread radioactivity where it falls, even if it is carrying a conventional warhead. In other words, a conventional impact by a reactor-equipped missile could still produce a level of radioactive contamination similar to a nuclear accident at the crash site. For that reason, some analysts argue that these systems are most likely to be used only with nuclear warheads. Finally, the development of such a weapon could trigger a new arms race. Many observers believe that the Burevestnik program, whether technically successful or not, raises serious strategic and safety questions for the future. There are two more points you should know about this missile. First, we still do not know exactly what type of jet engine Burevestnik uses. Some analysts believe it may be a nuclear-powered ramjet. A ramjet works slightly differently from the normal jet engine we discussed earlier. Explaining it properly would require a full video on its own, so we will not go deep into that here. Second, the system used in Burevestnik is an air-breathing engine. That means the engine needs air from the atmosphere to operate. Because of this, the same system will not work on a rocket in outer space since there is no air there. A nuclear rocket would need to carry a separate working fluid, for example, liquid hydrogen, to absorb heat from the reactor and expand through the nozzle to produce thrust. In that case, the vehicle still needs to carry a propellant, so the weight advantage becomes much smaller. I hope this video gave you a clear idea of how a nuclear-powered cruise missile works. If you liked this video, please hit like and leave a comment. For more videos like this, subscribe to the channel and enable the bell icon. Thank you.